In Chapter 14, we're going to expand our discussion to some more complex surfaces in three-dimensional space. The first thing we're going to do is go back to planes. And instead of just defining a simple horizontal or vertical plane, we're going to go ahead and define any plane. So to define any plane in space, all you need is a point and a normal vector. So imagine any vector in this plane. It's going to be orthogonal to the normal vector. So you take any orthogonal vector to our normal vector, and what we've done is we've generated our plane. And that's what's in this definition here. If you have some fixed point and a normal vector, then the set of all points for which this vector is orthogonal to n, that would generate our plane. So it's simply the normal vector dotted with any vector, so that it's equal to 0 since they're orthogonal. The equation we're going to use is in the box below. You just need a point and you need a normal vector. And if you have those two things, then the equation of our plane is going to be a times x minus x naught plus b times y minus y naught plus c times z minus z naught equal to 0. Now if we were to get rid of our parentheses, combine like terms, we can write our plane in a more efficient way as ax plus by plus cz equal to d. So below is our definition of our d. Now if we change that d value, what we end up with is a family of planes parallel to our plane. And then all parallel planes will have normal vectors moving in the same direction. In example 1, we're going to find the equation of the plane passing through this point 1, negative 4, 7 with a normal vector 2, 1, 2. So all we have to do is simply write our a value, which is 2, b is 1, and c is 2. So it's going to be 2 times x minus 1 plus 1 times y minus a negative 4, so y plus 4, plus 2 times z minus 7 equal to 0. So this would be the general equation, but typically we would get rid of our parentheses and combine like terms. So I'll get 2x minus 2 plus y plus 4 plus 2z minus 14 equal to 0. So moving all the constants to the right-hand side of the equal sign, our equation is simply 2x plus y plus 2z equal to 12. So this is the equation of our plane in space. Now we're going to find the intercepts and sketch the graph of the plane. So to find your x-intercepts, it's the same thing as what we would do in two-dimensional space. In two-dimensional space, to find the x-intercept, you set y equal to 0. In three-dimensional space, to find the x-intercept, you set both y and z equal to 0. So in our equation, if y and z are 0, we simply get 2x equal to 12, or x is equal to 6. So that means the x-intercept is the point 6, 0, 0. So our y-intercept happens when x and z are 0, which means y is equal to 12 in our equation. So we have the point 0, comma 12, comma 0. And then finally the z-intercept, that's when x and y are 0. So we get z is equal to 6. The point would be 0, 0, 6. So now that we have our intercepts, let's go ahead and graph our plane. So I'm going to make my three-dimensional graph. Now again, I am not the best at graphing, that's for sure. This is just a sketch. So we have our x, our y, and our z-axis. So my x-intercept is at 1, 2, 3, 4, 5, 6. And y and z are 0. The y-intercept would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And z would be at 1, 2, 3, 4, 5, 6. So typically when you're sketching a plane, you would just connect all of your intercepts, and that's it. That's how we sketch the graph of a plane, with the understanding that it goes infinitely in all directions. Right? So here's my plane. All right. So now what if we have 3 points, but we don't have our normal vector? Well, we know that the equation of our plane is passing through all 3 of these points. So you just have to choose one of these points to be your P sub 0 or your P naught. So I'll just choose the first point. And since I know that Q and R are also on the plane, all I have to do is figure out what the vector PQ is and the vector PR. That gives me 2 vectors in my plane. If I cross those 2 vectors, then I'll get my normal vector. So remember, PQ is simply Q minus P. PR is simply R minus P. So PQ is going to be 0, negative 6, negative 3. And PR is negative 1, negative 3, negative 2. So our normal vector is going to be the cross product, which would be our I, JK, vector of 0, negative 6, negative 3, negative 1, negative 3, negative 2. And when we compute our cross product, it looks like it's going to be negative 12 minus 9. So that gives me a 3i. And the next one should be a positive 3. It's going to end up being a plus 3j. And then a minus 6k after we compute the cross product. Or in vector notation, that would be 3, 3, negative 6. So what's really interesting here is we don't have to use 3, 3, negative 6. It's perfectly fine. But notice that if I factor out a common 3, I get 1, 1, negative 2. We can also use this 1, 1, negative 2 since this is parallel to our normal vector. And now the equation is going to be 1 times x minus 1, or x minus 1. So I'm using 1, 1, negative 2 for my normal vector. You could use 3, 3, negative 6. You'll find that you'll just have to do more simplifying later on. Plus 1 times y minus 2 minus 2 times z minus 3 equal to 0. And now doing some simplifying, I get x minus 1 plus y minus 2 minus 2z plus 6 equal to 0, or x plus y minus 2z equal to negative 3. Okay, so again, you need a point and you need a normal vector. Let's look at another example. Let's say we do have this plane, 3x plus y minus z equal to 6. So what if we wanted to find a normal vector to this plane? And that would be our part A. Well, all you have to do is simply look at the coefficients on the x, the y, and the z. So our normal vector that we're going to be using is 3, 1, negative 1. So the coefficients, going back to the definition, the a, b, and c, those are just the coefficients on your x, your y, and your z. In part B, we want to find our intercepts. So our x-intercept, that's a point, right? We're not using vector notation. That would be when y and z are 0, so that's 3x equal to 6, which means x is 2. So that would be the point 2, 0, 0. And our y-intercept, we set x and z equal to 0, and we have y is equal to 6, or 0, 6, 0. And then our z-intercept is when x and y are 0, so negative z is 6, z is negative 6. Part C is find the equation of the lines where the plane intersects the coordinate planes. Okay. So first of all, let me go ahead and do part D. I'm actually going to sketch the graph right now because I have my intercepts. It might be easier to see what C is talking about, part C. So we have 2. I'm going to pretend like this is 2. Y is 6, maybe about here. And z is negative 6. So we have our axis coming down. And if I were to draw the lines intersecting, the intercepts, that's what we're supposed to be finding the equations of in part C. These 3 lines that are intersecting are 3 intercepts. So here's our plane passing through these points. So if I just look at the xy plane, and I look at the line that's passing through the xy plane, that means it's going to pass through the x and the y intercepts. That would be this line that I'm drawing in red here. I find that when my z value is 0. So all you have to do is set the z value of 0 inside our equation, and you get 3x plus y equal to 6. Now if I look at the xz plane, what I'm looking at is I'm looking at the x and the z intercept. So So this line here that I'm tracing, I'm simply going to let y equal 0, and that gives me 3x minus z equal to 6. And then last, I'm going to be looking at the z and the y. Actually, I like y first because it's alphabetical. YZ plane. So if we look at the line that passes through our YZ plane, we simply set x equal to 0, and we have the equation y minus z equal to 6. So we have some really nice properties with planes. For one, if you have planes that are parallel, and that would be the first diagram, then their normal vectors are also parallel. So that simply means that they're scalar multiples of each other. So n sub 1 is equal to some constant c times n sub 2. If, as in the second diagram, planes are orthogonal, then their normal vectors will also be orthogonal. So that means if you take the dot product, they're going to be equal to 0, right? So here in our diagram, these normal vectors are orthogonal. And then the last property is that if you look at the angle between any two intersecting planes, they don't have to be orthogonal, they just have to intersect. We look at the acute angle between the normal vectors, and we compute it using the dot product. So if we have two planes that intersect, we don't look at the obtuse angle, we always look at the acute angle. Helps if I use a thinner line. Sorry, this would be our angle theta that we're looking at. Okay, so always the acute angle. So we're going to use these properties in example 4. We want to determine if the planes are parallel or orthogonal. If the planes are orthogonal, we want to find the line of intersecting. So orthogonal planes will intersect. Their intersection will be a line. Well, first of all, if the planes are parallel, then their normal vectors should be scalar multiples of each other. So if I look at these two planes, and if I look at this first plane, I'll call this normal vector n sub 1. Remember, it's just the coefficients of the x, y, and z, so that's going to be 2, negative 3, positive 6. Looking at this second plane, and I'll call this normal vector n sub 2, it's going to be 3, comma 4, comma 1. Notice that these vectors are not scalar multiples of each other. I can't come up with any number to multiply one so I get the other. So these planes are not parallel. So since they're not parallel, that does not mean they're orthogonal. They may intersect, but not be orthogonal. So if they are orthogonal, that means that the dot product of these two normal vectors should be equal to 0. So I'm going to compute the dot product, and that's going to be 2 times 3 is 6, plus negative 3 times 4 is negative 12, so minus 12, plus 6 times 1, or 6. since the dot product of the normal vectors is 0, these planes are orthogonal. So parallel, see if the normal vectors are multiples of each other. Orthogonal, see if the normal vectors have a dot product of 0. If these were not orthogonal, then at this point I would stop. But they are orthogonal. So I want to find the line of intersection. Now when we usually try to figure out where two equations intersect, we set them equal to each other. The problem here is that I've got 3 variables, but only 2 equations, which means I probably can't solve. So what I'm going to do is, now remember, we're trying to find the equation of a line in vector form, so we need a point and we need our normal vector. So what I'm going to do for the equation of the line which means I need a normal vector and I need a point, is I'm going to just let my x value equal 0. And this is a technique we often use in algebra when we have something like 3 variables but only 2 equations. Okay? So I'm just going to get rid of my x value. And I could have chosen the y value or I could have chosen the z value. But what that gives me is it gives me, if x is 0 in these 2 equations, it gives me these 2 equations. One would be 3y plus 6z equal to 0. And the other equation, sorry, that's a 0, would be 4y plus z equal to 1. So now I have 2 equations, 2 variables. Algebraically, I can solve that. And in this first equation, it looks like I can divide everything by a -3. So I get y minus 2z is equal to 0. Or in other words, y is equal to 2z. So now what I can do is I could substitute in 2z for y in the second equation. So again, this is just going back to algebra. That would give me 4 times 2z plus z is equal to 1. So 8z plus 1z, I have 9z is equal to 1. It looks like z is equal to 1 over 9, which is fine. Plugging that back into my y value of 2z, I have y is equal to 2 times 1 over 9. Y is equal to 2 over 9. So remember in the beginning I had set x equal to 0. So now I have this point 0, 1/9, or I'm sorry, 2/9, comma 1/9. So I have a point. Now I need a normal vector. So this is the fun part. What I'm going to do is I'm going to go back to the diagram of these 2 planes that are orthogonal. Notice that these 2 planes intersect in this line. If I were to move this line up, it would be orthogonal to the 2 normal vectors. So to find, remember all I need for a line is a point and a direction vector. So to find that direction vector, all I have to do is take the cross product of my 2 normal vectors n sub 1 and n sub 2. And that will give me my direction vector for my line. So my normal vector is going to be equal to the cross product of n sub 1 and n sub 2. And the direction doesn't matter. I could have done n sub 2 minus n sub 1, because remember, this is not a vector that I'm trying to find the equation of. It's a line. So it's going to go in both directions. So I'm going to have my I, j, k. And n sub 1 is 2, negative 3, 6. N sub 2 is 3, 4, 1. And when I compute this, it looks like I get negative 3 minus negative 24. So it looks like negative 27. I'm just going to go ahead and write it straight as a vector form. Minus a negative 16, so that should be a plus 16 minus 17. Which means the equation of my line is going to be my point 0, 2 over 9, 1 over 9, plus t times negative 27, comma 16, comma 17. And you could leave it in that form, or you can go ahead and combine this. I know oftentimes my lab will not combine them, but if you want to combine them, it should be negative 27 t, comma 2/9 plus 16t, comma 1/9 plus 17t. Okay, so we're putting together our discussion on normal vectors and our previous discussion on lines. The next thing we're going to do is move on beyond planes, and we're going to talk about cylinders and then traces. Cylinders that you discussed in your previous geometry courses were shapes like a soda can. But that's actually not the mathematical definition of a cylinder. A cylinder, by definition, is formed by any curve C. So if we look at this first diagram, we have this curve in red. This curve is in a plane P. Notice on the diagram I don't really have a plane P. So I'm going to draw what that plane is. So remember, the curve is in the plane. Notice that this surface is not a plane. So if you can imagine a plane that our curve is in, that plane is perpendicular to that surface that you see. So given a curve C in a plane P, and a line L not in P, so that's this black line here. This line L is actually not in the plane. It passes through the plane, but it's not in the plane. The definition of our cylinder is a surface consisting of all lines parallel to L that pass through C. So if you look at all lines that are parallel to L and pass through our curve C, you see how we're generating this surface. If we can generate a surface by parallel lines passing through C, then it's a cylinder. So this shape you see is actually the shape of a cylinder in mathematics. If our line L is parallel to a coordinate axis, then so is the cylinder. In such a case, the variable of the parallel coordinate axis is missing from the equation. So let's see what that means in this next diagram. So here in red I have my curve C. And I have all these lines passing through my curve C. Notice that all of these lines are parallel to the z-axis. Okay. So these lines are parallel to the z-axis. Since they're parallel to the z-axis, the equation of my surface is actually the equation of the parabola y is equal to x squared. Notice that y equal to x squared does not have a z variable in there because my surface is parallel to the z-axis. So in two-dimensional space, y equal to x squared is just simply that red curve. In three-dimensional space, if you use a 3D grapher such as Desmos, or I have a Mac, so I have a grapher that I've installed on my Mac. If you put in y equal to x squared, you'll get this surface in three-dimensional space. Okay, so let's look at a few properties here. Where the surface intersects the xy plane, notice that that's where my curve is. So I call that curve the xy trace. It's simply the intersection between the xy plane and my surface. That's how that curve is generated. Down below in this box, we define what a trace is. So a trace for any surface, and here we have a surface. Notice that the surface that I have below, that's actually not a cylinder. So a trace is just a set of points. It's going to be a curve where the surface intersects a plane. So a trace is just a curve where the surface intersects a plane that is parallel to one of the coordinate planes. If the trace is in a coordinate plane, then it's called the xy trace, the xz trace, and the yz trace. So you might have heard the term cross-section. That's another way to describe a trace. Looking at this first picture, notice if I intersect this shape with the xy plane, I end up with this ellipse. So this ellipse is the xy trace. Now, if I were to intersect with a vertical plane that is the YZ plane, I'll end up with this trace, which is a parabola. And then that would become my YZ trace. So if I intersect a shape with the XZ plane, I end up with a trace here that also looks like a parabola, and this would be our XZ trace. So a trace is simply the curve that you get when you intersect your surface with a plane, a specific plane that's either parallel to the XY, the XZ, or the ZY coordinates. However, if you're looking at the intersection with the XY plane, then it's an XY trace. With the YZ plane, it's the YZ trace. And with the XZ plane, it's going to be the XZ trace. So these traces or cross sections, we typically use it to help us graph and get a better idea of the picture of our equations. Example 5, we want to sketch the graph of this cylinder x squared plus y squared equal to 25, and then identify the axis to which the cylinder is parallel. Well, I already know what axis the cylinder is parallel to, because notice in my equation there's no z value. And since there's no z value, I know that it's parallel to the z-axis. So I get that right away. Okay, so we've identified the axis to which the cylinder is parallel. Now I want to sketch the graph. So the first thing I'm going to do is draw my coordinate system. So I know parallel to the z-axis. What I'm going to do now is I'm going to try to find the xy trace. So to find the xy trace, we're letting z equal 0. And I have x squared plus y squared is equal to 25, which is a circle. The center is 0, 0, and it has a radius of 5. On my graph, let's see, it's about 5, about 5. I'm going to sketch my circle. You got to forgive me because I'm not a very good artist. So there's my xy trace. Now I already know it's perpendicular, or it's parallel, sorry, to the z-axis. So I'm thinking this is a traditional cylinder that just kind of goes up like this. Well, that is a very, very sad graph. But I'm going to double check by looking at the other traces. If I look at the xz trace, that just means that I'm letting y equal 0 in my equation. That gives me x squared equal to 25, or x is equal to plus or minus 5. And that makes sense because these are simply lines. Going back to my graph, I'm going to go to 5, right? This was 5. And I'm going to draw my line. I'm also going to kind of erase. Oh, I can't do it. And then if I were to go to 5 on the other side and draw my line, right, so I can see that this is probably going to end up being a cylinder. Oh, that's the worst drawing I've ever made, I think. But let's go ahead and continue to verify by finding the YZ trace. So if I find my YZ trace, that would be when x is equal to 0. I'm thinking that I should also have vertical lines passing through my y-axis, which I kind of already have. So that means y squared is equal to 25, y is equal to plus or minus 5. And again, we have these lines, and I've already got one of them already. And continuing on with our y-axis, probably about here, I will continue to have these lines. So there's my sad cylinder. If I were to describe this, this is a traditional cylinder. It's parallel to the z-axis. And that's actually important because if it's parallel to the z-axis, and here we can look at the center as being the usual center, then that means that there's symmetry about the z-axis. However, just because something is parallel to an axis does not mean that symmetry there. What I mean by symmetry is that if I take any one of these lines and I rotate it around the circle, rotate this 5 away from the z-axis or around the axis, then what I get is I get my cylinder. So generating any one of those lines around the z-axis will give me my cylinder. So in general, a plane is a cylinder, but not all cylinders are planes. It's like a square is a rectangle, but not all rectangles are squares. Well, now all cylinders are what we call quadratic surfaces, but not all quadratic surfaces are cylinders. So we're getting into more complicated surfaces. Now, a quadratic surface is called a quadratic surface because at least one, doesn't have to be all of them, but at least one of the variables x, y, or z, highest exponent will be a 2. So you could think about a quadratic equation from algebra. We have an x squared or a y squared. Well, now we have quadratic surfaces where x, y, or z is squared, possibly 2 of them, possibly all of them. So this long, nasty thing is the general form of an equation of a quadratic surface. We're going to look at some common quadratic surfaces that come up. The first one is this ellipsoid, and our quadratic surfaces are described by their traces. Notice that if I cut through this ellipsoid with the xy plane, I get this trace that's an ellipse. If I cut through the xz, I also get a trace that's an ellipse. Now these common surfaces that I'm looking at happen to be kind of centered at the origin, but they don't have to be. And in fact, notice that this ellipsoid is elongated on the y-axis. So actually there is symmetry about this y-axis where if I say take this trace and I rotate it about the y-axis, it'll generate my ellipsoid. But I can also look at ellipsoids that are elongated along the z. That's my diagram for an ellipsoid. I can also look at ellipsoids that are shifted. And in that case, there would be no axis of symmetry. So these are just simply shapes. Think of them as having centers or vertices at the origin. If I do have an ellipsoid, its general form is given by this equation here. The x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. Equations of this form will have all traces that are ellipses, which is why it's called an ellipsoid. Okay? So the traces are generating the shape. Now, if this were not centered at the origin, then our x squared, y squared, or z squared may be written a little bit differently. So for instance, if I had a center of 1, 1, 1, then maybe this would be x minus 1 squared over some value a squared, plus y minus 1 squared over some b squared, plus z minus 1 squared over some c squared equal to 1. So yes, we can shift them. Okay? It just changes the equation, changes your x, y, and z. The next common shape is an elliptical paraboloid because the traces are either ellipses or parabolas. This particular elliptical paraboloid has symmetry about the z-axis. Notice that if I were to cut through this with any plane parallel to the xy, I would end up with traces that are ellipses. However, if I were to intersect this surface with a vertical plane, I would end up with traces that are parabolas. So note that this particular elliptical paraboloid is symmetrical about the z-axis, but it doesn't have to be. We could look at elliptical paraboloids that are symmetrical about the y-axis or about the x-axis. So notice in the general equation, the x squared over a squared plus y squared over b squared equal to z. And it's symmetric about the z. So if we get rid of the z value or replace the z value with some number, what you end up is with equations of the ellipses. In the event it was symmetrical about the y-axis, this would be an x squared over a squared plus z squared over b squared equal to y. So what it's equal to is where the symmetry is, assuming the vertex is at the origin. The next shape we're going to look at is an elliptical or elliptic cone. The equation of an elliptic cone is x squared over a squared plus y squared over b squared equal to z squared over c squared. Notice the x, y, and z are all squared. This is symmetrical about the z. Notice the equation is equal to the z. However, we could have a cone that is symmetrical about the y-axis, and in that case the equation would be equal to the y squared over c squared. So our traces, if we were to chop it with a plane in this particular diagram, a horizontal plane, the traces would be ellipses. However, if we were to chop this with a vertical plane, what we would end up with is we would end up with these hyperbolas. Sort of. Looks like a hyperbola. But it's actually these intersecting lines. So that's an elliptic cone. The next shape we're going to look at is a hyperboloid of one sheet. The equation here is going to be x squared over a squared plus y squared over b squared minus z squared over c squared is equal to 1. What you're subtracting is where the symmetry is. And then moving on, we have a hyperboloid of two sheets. So the only difference here is there's this space between the upper and the lower in this case. So notice that the axis of symmetry in this case is the term that's positive. We have a minus x squared, a minus y squared, but it's a positive z squared. Again, remember, we can always shift these. They can always be symmetric about different axes. The last shape we're going to look at, the last common shape, is this saddle shape. So a saddle is a hyperbolic paraboloid, and the equation y squared over b squared minus x squared over a squared is equal to z over c. So this has this weird symmetry. About the z-axis, not really a symmetry. What you notice is that it passes through the origin, but I don't know if you could tell from this diagram, that is the only point that crosses the z-axis in this particular case. So if we're looking at some cross sections, you can see we have these parabolas. But if we were to take horizontal planes and cross through, that would give us our hyperbolas. I know it's kind of hard to see, but we get these hyperbolas, which is why it's called a hyperbolic paraboloid. So this last example, we have this equation. I noticed that I have an x, y, z. I have some squares on my x's, my y's, and my z's. So I'm thinking that this is a quadratic surface. To identify this, what I want to do is complete the square on the y values in this case, because I have a 2y and I have a y squared. And then try to get it into one of the forms that we saw previously. So the first thing I'm going to do is bring my y's next to each other and complete the square. If I had any constants, I would move them all over to the right. So I get 9x squared plus, if I complete the square, I need to add 1. So the y squared plus 2y plus 1 becomes y plus 1 squared. So if I add 1 on the left, I have to add 1 to the right-hand side. And now I have 9x squared plus y plus 1 squared minus 4z squared equal to 1. All right. So the last thing I want to do, it's already equal to 1, and I see I have x, y, z are all squared. So what I want to do is make sure the coefficient on my squares is 1. I'm going to divide top and bottom by 9 to get x squared over 1/9 plus, this is y plus 1 squared over 1 minus z squared over 1/4 equal to 1. So this is an x squared over a squared plus y squared over b squared minus z squared over c squared equal to 1. It has the form of a hyperboloid. Of one sheet. It's parallel to the z-axis because it's a minus z squared. I could also say what line it's rotating around. because it has this weird center, 0, -1, 0, right? All I'm doing is figuring out what x, y, and z gives me 0. Then the line passing through this point and parallel to the z-axis, so I can look at a direction vector as being 0, 0, 1. So that would be the line 0, -1, t. So I know that this hyperboloid of one sheet is actually rotating around the line r of t equal to 0, -1, t. Now I'm not sure if my lab will be that specific when you're describing the shape, but I decided it should just be as specific as possible. So that's it for this section.